Hello everyone. So in this lecture, we're going to talk about the drag and lift forces on in external flow. So in many engineering applications, there are fluid flow over solid bodies. And the fluid flow over solid bodies is responsible for numerous physical phenomena such as drag force acting on automobiles, power lines, trees, and underwater pipelines. Also, there is a lift force, the lift developed by bird or airplane wings. So there is an upward draft of, for example, upward draft of rain, snow, hail, and dust particles in high winds. The transportation of red blood cells by blood flow, the entertainment and disbursement of liquid droplets by sprays, the vibration and noise generated by bodies moving in a fluid, and the power generated by wind turbines. These are types of lift forces and examples of lift forces. So if we know if you have a good understanding of the lift forces and drag forces, it helps us to design, to provide a better design or improve the current designs of the mechanical systems. So the good example of the drag force can be demonstrated by looking at different types of cars, different car design. So in late model cars, we see an improved form of design. So they have been designed with particular emphasis on aerodynamics. And this design has resulted in significant reductions in fuel consumption and noises, and considerable improvement in handling of the machine. So for example, here, if we want to keep 60 miles per hour speed, we may need to use 70 horsepower. But here, with the same velocity, we may need to use much less amount of power because of the shape, improved shape, and a certain aerodynamic form of the car. So sometimes, so not always the solid body or the object is flowing inside the fluid or against the flow. Sometimes a fluid moves over a stationary body, such as the wind blowing over a building, and other times a body moves through a stationary fluid, such as a car moving through air. So these two seemingly different processes are similar, are equivalent to each other. What matters is the relative motion between the fluid and the body. And such motions are conveniently analyzed by fixing the coordinate system on the body and are referred to as flow over bodies or external flow. So one of those forces is drag force. So we want to start with the drag and then we go to the lift force. Drag force is the reason why in the real world, if we drop a feather and a rock from the same height, they would never reach the ground at the same time. Even though the gravitational force acting on them is exactly the same. So the drag force, as known as air resistance typically, is caused by all the gas molecules in the air. We cannot see it, excuse me, obviously, we cannot see it, but that doesn't mean that it doesn't exist. Think of it like water. We have to push away the water molecules when swimming. The same concept applies to air resistance, except we barely feel any of that resistance in our daily life. However, when we move at a greater speed, we start to feel more and more resistance, air resistance. The direction of the direct force is always opposite to the direction of the velocity of the object. So it's always against the motion, against the movement, direction of the motion. What about the lift? The lift force is basically typically helping the motion of the object, or typically that's how we take advantage of it. Lift is the force that directly opposes the weight of an airplane and holds the airplane in the air. Lift force is generated by every part of the airplane, but most of the lift on a normal airliner is generated by the wings. Lift is a mechanical aerodynamic force produced by the motion of the airplane through the air. Because lift is a force, it is a vector quantity having both a magnitude and a direction associated with it. And lift acts through the center of pressure of the object and is directed perpendicular to the flow direction. So the mathematical formulation of lift, the simple mathematical formulation of lift and the drag force are as follows. So as you can see in here, you have, let's say you have an airfoil. So in the airfoil, there are two main directions of the forces, drag and lift. The force against the, let's say that we have a flow over the airfoil, or airfoil is moving horizontally on the inside a fluid. So the drag force is horizontal, is against the motion, and against the motion of the airfoil, and the lift force is perpendicular to horizontal directions. So when we want to calculate the lift force and the lift force and the drag force, we need to calculate the lift force and drag force for every small piece of the surface of that object. So that's why you see the differential equation. DFD, so a small, the drag force related to a small surface over this airplane, airfoil, I'm sorry, is equal to the air force, is equal to the drag force as a result of having pressure and also shear stress. Pressure is typically perpendicular as a result of perpendicular force. Shear stress is as a result of non-perpendicular, parallel force. So if we integrate these, and the same for lift. So lift is the force perpendicular to the motion of the object. The total drag force and the total lift force can be calculated by integrating these two equations over the entire surface of the airfoil. So if we calculate it, so this is what we have. This is what we have. So drag force, as you can see, as a result of two forces, the shear stress that can be interpreted as friction, and the pressure, the force against the motion also, and the lift force. So these are the mathematical form of the lift and drag force. But more general equation can be developed, so is already developed. So we want to work with two, instead of using these equations, these general equations, we want to use more like simple equations for the drag force as lift force. So we use the drag coefficient and the lift coefficient because it's always convenient to work with appropriate dimensionless correlated to a mechanism, mechanical systems. These are two dimensionless parameters that we use to calculate the drag force and lift force. The drag coefficient is equal to the drag force for that specific motions divided by 1/2 times density times velocity squared times area. What is this area? Area is a frontal area. And you've seen an example that what that frontal area means. So for example, here, the frontal area is the area that a person who is standing in front of the airfoil can see. So the frontal area is the cross-sectional area of this airfoil. So let's say the person is standing right in front of the airfoil, not at the side, in front of the airfoil, somewhere in here, and look at this airfoil. So the area that he sees or she sees is a small area. So cross-sectional area. So the area would be something like this. Let's say airfoil is depends on the shape of the airfoil. So like this, if someone look at the airfoil from the front side, this is what he or she sees as an airfoil, not this side. So, and it depends on the airfoil. Airfoil may be very wide. If it's very wide, then what the person sees is something like this. When she or she is looking at the airfoil from the front side. Okay, front side. So area is a frontal area. Okay. Lift coefficient is for the calculation of the lift force is equal to lift force divided by 1/2 density times velocity squared times the area, again frontal area. So the area that you can see when you are standing in front of the object, not at the side of the object. Also, we can use this correlation. You don't want to use it that much. These two equations, if you want to calculate the average drag force over a certain length, but we don't want to use this equation that much. So if you reform it, the drag coefficient, this is the drag force and this is the lift force coefficients. Also the drag itself, the drag force is a force exerted by fluid on a body in direction of the flow due to the combined effects of wall shear and pressure force. That's what I mentioned in here. So you have pressure component and shear component. You have pressure component and shear component. The same in here. For lift force also, you have pressure and shear component. That's why we may resolve the drag coefficient into drag coefficient correlated with the friction and the drag coefficient correlated with the pressure. The friction drag is the component of the wall shear force in the direction of the flow. So it depends on the orientation of the body as well as the magnitude of the wall shear stress. For parallel flow, for example, for parallel flow over a flat plate surface, the drag coefficient is equal to the friction drag coefficient. And the friction drag is a strong function of viscosity and increases with increasing the viscosity. but we don't see that effect inside these general equations. So the part of the drag that is due directly to the wall shear stress is called a skin friction drag or just friction drag, since it's caused by the frictional effects. And the part that is due directly to pressure is called the pressure drag, also called the form drag, because of its strong dependence on the form or shape, on the form and shape of the body. So the CD that you see in here is basically a combination of these two, CD as a result of friction and as a result of pressure. Or if you can calculate the drag force as a result of friction separately and the pressure separately, you can add them up and get the total drag force. Let's solve one example, and this is the only example that you see for this lecture. The drag coefficient of a car at the design conditions of 1 atmosphere, 21 degrees Celsius, and 1 kilometer per hour is to be determined experimentally in a large wind tunnel in a full scale test. The frontal area of the car is 2 meters square. So what is this area? This area is the area that you can see when you look at the car from the front side. So when you stand in front of the car, not at the side of the car, when you stand in front of the car and look at the car, that area is the frontal area. If the force acting on the car in the flow direction is measured to be 300 Newton, what is the drag coefficient of this car? So this is experimental setup, but is a full scale. So we assume that the bottom of the tunnel is also moving at the speed of the air to approximate actual driving conditions, and or this effect is negligible. Properties. The properties of the water, the density of the water is what we need, the only property that we need. Of the air at 1 atmosphere and 21 degrees Celsius is 998.02 kilogram per meter cube. So how do we calculate the drag coefficient? The drag coefficient is, so the drag coefficient can be calculated using this equation, because this is a general equation to calculate drag force. So this is the equation to calculate the drag coefficients. The drag coefficient is equal to 2 times force divided by rho AV squared. V is the velocity, it's not a specific volume, it's a velocity in here. 2 times 300, density is 998.02, and times the times 1,000, because it was 1 kilometer per hour, 1,000 per 3,600, so I change it to meter per second, and the result is 7.8. This is a dimensionless coefficient. And A, again, is a frontal area. So this is a lecture for chapter 15. This is it. The next session is going to be exam. Exam is going to be on the chapters, the fluid part of the course. So whatever that we talked about since after the first exam through the end of this lecture. So what you need to do is study all the lecture notes, all the chapters that we covered after this first exam, all the examples and practice problems, if there are any practice problems. I also uploaded the solution manual for the practice problems. Were not the examples on the book. So I uploaded the solution to the practice problems that were end of chapter homework, end of chapter problems. So you didn't have access to the solution if I didn't upload them. Just read them, and the exam is going to be, as I said, is going to be uploaded sometimes on Thursday. Thank you very much and have a great week.